Welcome back. This is the third video that introduces time series techniques. So what I'd like to do in this video is to cover various transformations that you do to the data before you fit any sort of model. Okay, so the absolute first thing that you should do is make sure that your data is comparable. Okay, so as an example, if we have data by the month, February only has 28 days, while March and January have 31 days. And so often you'll see that your sales or whatever are lower in February, and it's not because something happened in February. It's because there are 3 fewer days in February than there are in March and January. Okay, so I call this the February effect. Another example of this. Sometimes you'll only get part of a month. Maybe you only get the first 3 weeks, and then they send you the data, and you're missing the last week. So if you look at that 3-week period, it looks like your sales are much lower for the current month than they really are. And so the simplest way to make sure your months are comparable is just to divide by the number of days in the month. And so R actually helps you with this by providing a function called month days that would give you 31 for January and 28 for February when it's not a leap year. Another way that we make data comparable is to adjust for population size. So I'm just going to take us over to the newspaper right now. And so this happens to be the Washington Post, and what you're going to see is everything is kind of normalized per 100,000. Okay, so Arizona has this number of cases per 100,000, and that kind of puts on equal footing. You don't want to, it would look like New York has way more cases than, say, Arizona, just because there's more people living there. And by dividing by the population size, or in this case by population size times 100,000, you get more comparable numbers. All right. So that's another way that we would transform the data prior to any analysis. Another really important thing to keep in mind whenever you have dollar amounts over an extended time period is that there's inflation. So, $10 20 years ago was worth a lot more than $10 is worth today. So we need to make those adjustments, and so we usually will end up dividing by some inflation rate or a consumer price index to take that into account. If I have a long time series with dollar amounts or any sort of currency amounts. Another transformation that we may want to do is to ignore certain seasonalities. So I've already mentioned this in a previous video, but we can use the aggregate command to get rid of, for example, time of day effects or day of week effects. So just take us back to the newspaper here. When we look at COVID cases, looks like we have more cases during the middle of the week than on weekends. If we're not really interested in forecasting specifically how many cases get reported on a particular day, we'd be better off just summing cases over the entire week, and that would get rid of that seasonal effect. Another type of transformation that we may want to do is to look at differencing. Okay, so differencing we talked about in, I guess it was 2 videos ago, or maybe it was the last video. All we're doing is we're taking the value for the current period and subtracting the previous period. The way I like to think of this is it's kind of a discrete version of the first derivative. You're saying how much is y changing over time. And so, for example, we're going to be analyzing COVID data in this class, and we're going to take it right from the New York Times GitHub website. What they report is the total number of cases that have occurred as of this date. All right, so that's what y sub t is. Now, when we go back to a graph like this isn't showing the total number of cases that have occurred as of this date. this is actually showing difference data. This is like how many new cases occurred on each of these days. Okay, so this is going to be the total number of cases as of midnight, tonight, minus the total number of cases midnight yesterday, gives the number of new cases, which would be a first difference. So very often we're going to want to analyze first differences. Keep a key fact here, just like we can go from the derivative of a function back to the original function through integration, we can go back to the original series if we want to know the total number of COVID cases or whatever, by summing the differences. Summing is just like integration. So often using the difference data will solve a lot of problems for us. And so we go to difference data to avoid problems with, for example, autocorrelation of our errors. We go fit our model, then we go back to the original data with another transformation after we've estimated our model. So that's a really, kind of important technique that we're going to be using with time series. I mentioned about reducing autocorrelations. Another thing that we often do is to analyze differences to strengthen internal validity. So in a previous course, you probably did some difference in difference models. So you can go click on this page if you want to go read about difference in difference models. But what that does is it takes out the effect of having a different y value in, say, your treatment and control group prior to some treatment. So if you look at the change, it's like you've taken out where you started out. Right? The starting level has been equalized in a sense. And so this is going to give us better internal validity by doing that. Occasionally, we're going to want to go further and take second differences. So these are going to be differences of the differences. This is going to be analogous to a second derivative back in calculus. Usually we don't go beyond second differences, but in theory you could even do third order differences. But I've never done that, to be honest with you. All right. Now I want to move on to another class of transformations that we may want to take prior to an analysis. And these transformations have a number of names. So they're either called power transformations or Box-Cox transformations. I've called them Tukey's ladder of transformations in my regression videos. The purpose for these transformations is to stabilize the variance. So, in a previous video, we saw how Amazon's sales are increasing over time, and the variation around the trend was also increasing over time. So we're gonna look at that picture right here. So you can actually see how the amplitude of that seasonal effect increases over time. And so the way we're going to deal with that is by transforming y. And this is very similar to what we did back in regression when we took a transformation of y to stabilize the variance. So it's called a variance stabilizing transformation back in regression. That's exactly what we're doing here. And so what we'd like is not to have to deal with the amplitude of seasonal effects changing over time, because that's going to make our life really complicated. And so if we go back and look at this picture, notice the amplitude of that seasonal effect is fairly small, and it gets bigger as the mean of sales increases over time. All right, so what we're going to end up doing is taking a transformation of this to stabilize that variance, so we don't have to come up with some complicated model of how it changes, of how that amplitude of the seasonal effect is changing. All right, so how do we do this? Well, it's a lot like what I told you to do in regression. What I told you to do in regression was, if the variance is increasing with the mean, as we saw with Amazon, basically what I told you back in regression was take the log or the square root. And so what I'm going to tell you now is maybe a slightly more nuanced version of this. So the power transformation An example of this would be the square root function is one way to address this. Let me just kind of take us back to what I said with regression. So go watch the entire video that I did on regression around this. But basically, I was talking about power functions here. K was this was the magnitude of the exponent, and what I said was if you go up Tukey's ladder, so you increase the power, the slope of this curve gets stronger and stronger. As you decrease the power, the slope of the curve gets flatter and flatter. It goes to zero faster as I decrease K. Then back in that video, I said, what do we do about x to the 0? And I said, well, we're going to insert the log function there. All right. And I gave a rationale for why that would be the case. If we think about this in terms of the derivative and you integrate this function, you end up with something reasonable. So watch that video if you don't remember that stuff. All right, so the Box-Cox transformation is just a further kind of generalization of what I was describing with power transformations. Okay, so the Box-Cox transformation says just take the log of y if your hyperparameter lambda is 0. Otherwise, what you're going to do is basically raise y to the lambda power. So if lambda were a half, you'd get basically the square root, as you did with the power function. Now we've subtracted 1 and we've divided by a half, so we've adjusted a few things, but it's basically the square root function. Okay, so instead of having discrete steps the way I described Tukey's ladder, what Box-Cox does for us is it allows this lambda to be on a continuum. So back on my ladder, I could only have powers of, say 0, 1/2, 1, 2, and so forth. If you think of discrete rungs on a ladder, with Box-Cox, we can have this be a continuous, power. And all right, so there's actually a function in R that will give you a reasonable lambda value. Okay, so it will do this to try to make the seasonal variation roughly the same over the time series. So let me illustrate this with the Amazon data. So here is our Amazon data, and if we do an auto plot, we see the seasonal effects with varying amplitudes over time. I eyeballed this and said, I think I'm going to need a log. And so if you auto plot the log of Amazon, notice your trend is pretty flat. It's like it's not flat, but it's a straight line. So rather than having this increasing pattern, it's a straight line. And so exponential growth is when you take a log of the function and you get a line. Right? And so we're kind of close to exponential growth, and that's what I suspected back in the first video when I first showed this data. But is that really the optimal lambda value to produce the same amplitude across the whole plot? Well, we can use the Box-Cox lambda function to estimate the optimal lambda. And what you're going to see is the optimal lambda is about 0.17. So the way to think about this is it's actually fairly close to 0. So remember, a lambda of 0 is the log function. A lambda of 1 would mean don't transform it at all. And so what this is saying is you almost want to log it. Now the fact that it's a little positive is telling me the log is maybe a little too strong. Okay, it's too strong of a transformation in that you see that we've gone from kind of one problem where the amplitude gets bigger over time to where the amplitude is actually shrinking over time. So that's a signal that the log is just a little bit too strong for it. And so this bottom plot down here, so I can apply that lambda that I estimated with the Box-Cox function. And so this one would be a little bit, it doesn't quite shrink the amplitude as much as the previous one. All right, so that's an illustration of using the Box-Cox function. So Box-Cox.lambda determines the optimal lambda. You could either type in this function or just use the Box-Cox function with the lambda argument to do the transformation for you. At the end of the day, you're going to want to transform it back with this inverse Box-Cox, which undoes the transformation for you automatically. More on this in a second. Just a couple things. Your textbook by Heinemann and I recommend using simple lambda values. He doesn't really say what he means by a simple lambda value, but what I would take from that is nice round numbers like a 0, which would be log, or 1, which is nothing, or a half, which would be a square root. I especially like the log function because it has this property that it turns a multiplicative model into an additive model, as I suggested back in the first week of the first video. I went over that. Okay, so I kind of prefer logs in a case like this where it's 0.17. I'd round down to 0 and go with the log, if that makes any sense. All right. Finally, there's an additional term, which is this bias adjustment. So you have to tell R when you transform back whether to do a bias adjustment. So what does this mean? In order to understand this, we need to recall some properties about the log normal distribution. By the way, I have a video on this, on the multiplicative regression model, that is worth watching. So I would I'd recommend you watch this if you didn't take my earlier class. Okay, so let me just give you the headline, and then I'm going to try to give you a little bit of intuition behind why this is. Okay, so if you say bias adjustment equals false, then it's going to return the median of y. But if you say bias adjustment equals true, you're going to get the mean of untransformed y. So the difference here is we're going to take the exponent of the transformed w versus the exponent of the transformed w plus a bias correction term, sigma squared over 2. So this is if I'm assuming I'm using the log transform right now. So why do we have to worry about this? Well, this was part of my earlier course packet, but I really didn't go into a lot of detail on this. Let me go into more detail today. So let's just say that y has a normal distribution, and it has some mean and variance. If you exponentiate y, you get what's called a log normal distribution. So it's called a log normal distribution because if you log this y star thing, you get y back, which is normal. So the log of this distribution, log of a log normal, is just a normal. Now, in a probability theory course, when you study moments and moment generating functions, one of the results that you would prove is that the mean of this log normal distribution isn't just the exponent of mu, it's the exponent of mu plus some function of the variance. And what I'd like to do now is try to give us a little bit of intuition behind why that is, why we would do this. So I just clicked on that link, and what we get is a picture of a log normal distribution, assuming a mean of 0 and varying the variance parameter. Okay, so the red distribution has very small variance. The green has variance which is larger. So the standard deviation is 0.25 for the red, 0.5 for the green, and 1 for the blue distribution. Now, what I'd like to just kind of suggest is that the mean of the blue is going to be bigger than the mean of the red. So what is the mean of the red? Well, remember that's the center of gravity, and there's not much of a tail here. The red distribution does not have a tail. And so there's not a lot of tail to pull out the mean. And so the mean is probably going to be just a little bit above 1. However, with the blue distribution, there is a very sizable long tail with a lot of mass in it that is going to pull the mean out. Okay, so because there is a greater mass in the tail, that's going to kind of pull the mean out. So let me go over to my scratch pad and try to emphasize this with a little bit more of a picture. So this is the distribution of y. And so let's just say for now, we're going to follow what was in Wikipedia. The mean here is 0, and the variance of this distribution is sigma squared. Now let's go make ourselves the log normal version of this. So this is the log normal version of it. Y star is equal to e to the y. And there's a very special value, which is 1. Okay, so why is 1 so special? Well, e to the 0 is equal to 1. Okay, so the mean of this distribution of 0, the mean of the original distribution of 0 was 0, and therefore, if I exponentiate that, that's the middle. By the way, that 0 is also the median of this distribution. So half your area is here and half your area is here. And so if I, when I take the exponent of this, I go from 0 all the way out to negative infinity. So let's just write that out here. And I take that whole area from 0 to minus infinity, and all of that gets squashed in this little region between 0 and 1. All right, so this is, for y less than, greater than negative infinity, less than or equal to 0. So this is 50% of my distribution, and then the other half of the distribution is going to get spread out here. So the y, and as I take the exponent of y, and that's going to become very big numbers. And so half of my area gets squeezed into this little bit. The other half of the area gets squeezed into the other bit, and it looks something like this. All right, now, what's important to note is that as the variance of the original distribution grows, this tail gets bigger. So there's more mass in this tail. And by the way, the mass in the other tail gets bigger. But a thick tail over here doesn't have much effect because it's getting squeezed into the 0-1 interval, the interval between 0 and 1. All right? Whereas a thick tail up here is going to have a lot of effect because that means there's a lot more mass out here, which is going to pull the mean out. All right, so when we go back to the Wikipedia page, what you're going to see is that the median is just e to the mu, while the mean is a function of both the mean of the original distribution plus the standard deviation of the original distribution. And so that's what I was saying here. The mean of this blue distribution is going to get pulled out because of that thick tail. The red distribution is not going to have that effect because there's not much of a tail there. All right, so back to the course packet. When you say you don't want a bias adjustment, you just get the median. And Heinemann, I think, mentions how in some ways that's a more kind of conservative way to go. Just using the median as the forecast may be a better way than using the mean. And that would be the value that you get without the bias adjustment. All right, so I don't have a strong opinion on whether or not you use the bias adjustment, but that gives us a little bit more background on what it means. So without the bias adjustment, you get the median. With the bias adjustment, you get the mean.